For those who don't know me, my name is Samir Kouro. I am from Chile. I work at the Universidad Federico Santa Maria in the Electronics Engineering Department, and I'm also a visiting scholar at the Universidad of Sevilla in Spain, where we have currently 40 degrees Celsius. So we're here you can really feel how the world is heating up. So I'll be talking about this paper included in the special session Professor Fred Blabjer introduced. So it's about charging infrastructure and grid integration for electromobility. This effort was led by Dr. Rivera from TU Delft, and I was really happy to join this very interesting team of colleagues in preparing this paper that I hope you like. So one of the issues with transportation is that it's one of the major contributors to greenhouse gas emissions, which is a cause of climate change. And this is forcing, of course, an energy transition in the sector. You have already seen one, which is the electric aircraft introduced by Professor Pat Wheeler. But of course, there is way more related to electrification of transportation. And here you can see some of the challenges that we're facing. But because of time and also the scope of one paper, we are covering in this one everything relating to the charging infrastructure for electric vehicles and plug-in electric vehicles, including also industrial electromobility and buses, which are heavy-duty vehicles. So that's the focus of this presentation. And there has been a very steep growth of 40% on an annual basis in the adoption of electric vehicles. As you can see here, these are the latest data from the International Energy Agency. And last year was a really good year. 14% of all car sales were electric, and 2.1 of the current car stock in the world is also electric. So we're getting there. But there's still a lot of market barriers. So there's, especially in many countries, this is not the true. Even Europe is 40% of sales last year were electric, but globally it's 14. So this means in some countries that's not the case. So there are a lot of market barriers. I'm going to focus only on those that are related to charging infrastructure. We cannot go on all of them. But vehicle cost, range and autonomy and maintenance are actually one were barriers that were initially tackled and are now getting by. Cost is a little bit high still in some economies, but range and autonomy is quite good right now, and maintenance is actually cheaper in electric vehicles compared to the internal combustion engine. So, but when we get to charging infrastructure, and we look into standards and regulations, we can really start looking at the challenges, right? We have a lot of standards. There is a kind of a convergence going on nowadays, but still we have a lot of them. And we have different voltage level, different power levels, different communication protocols, and also different connectors, both for AC and DC. So this is still perceived by some skeptics as an issue. And if we go to the chargers themselves, so to the charging infrastructure, you can see that there are not even 2 million slow chargers available around the world, most of them concentrated in China. And if you go to fast chargers, which are the ones that you would see in replace the gas stations, if you will, we don't crack even the million worldwide, and most of them again in China. So this is really perceived as an issue by some people trying to adopt electric vehicles. Charging times, also related to the power level of the charging stations, is an issue. So most of the charging stations, even the fast ones, would get your car charged in between 20 and 30 minutes, which is not comparable to what you can do with an internal combustion engine. So that's also perceived as an issue. And then most of the cultural related issues to adoption are also related to charging infrastructure. So range anxiety, people don't see the same amount of charging stations compared to gas stations. So where are the chargers? That's an issue. Or why would it be an issue to just use overnight charging like we do with our cell phones? So we do it with our cell phones and many other electronic devices. Why is that a problem with a car? Why do we need to actually put energy in our cars sufficient for the whole week or the whole month? So that's just a cultural issue that needs to be dealt with. So all of them are related to charging infrastructure, and this is why so much effort is being paid in advancing charging infrastructure. And here you can see 3 ways in which we get from the energy from the grid to the car. even if the energy matrix is not fully renewable, and we have a lot of coal or gas and fossil fuel in our energy matrix, it's still more efficient to burn it in an optimized way, similar to what Pat presented in the electric aircraft or the hybrid electric aircraft, and then transport the electrons to a charging station and then charge your batteries. And that could be done, like I said, overnight at home, or opportunity charging, which be at work or when you're in the supermarket or in the shopping mall or whatever. And then the DC fast charging stations, that would be to get you along the way for that very long trip you do once in a while, right? That would be a range extender. So these are like the three methods people would actually use them. Now, if we see them in terms of a configuration, we have then AC chargers, which are the orange ones here in the slides, or DC chargers, which are the blue ones in these slides. And here you can see the power levels that go from a few kilowatts, which is the onboard charger you do at home, to even a megawatt level for heavy-duty vehicles. And as you can see, there are quite a few standards out there. Now, if we look at them in terms of power electronics architecture and whether the converter is on board the electric vehicle or off board the electric vehicle, we have this slide over here in which we can see 6 types of main configurations. The dashed line divides whether it's off board, so outside the vehicle, or on board the vehicle. And the first one would be the onboard charger, which is AC. You connect to the AC grid at home. You have a DC converter, and then you have an isolated high frequency isolation stage that controls the battery, the energy going to the battery. Then you could have also an integrated AC charger that uses part of the powertrain of the vehicle, the motor and the inverter that usually drives the motor, to actually charge the battery. And then we have half of the charger outside and half of the charger on board that would be wireless or induction charging, which you would have like half of the coil outside and half of the coil inside the vehicle. And then we go to the off-board types, in which we have DC charging and one with the low frequency transformer at the grid side, or high frequency DC stage controlling the battery charge. And then we have everything outside the vehicle, including the battery, that would be battery swapping. So you charge a battery outside the vehicle, and then you just go to the charging station and you swap batteries, and you're good to go. So all of these have advantages, disadvantages, and of course they have different power ratings and charging times. Being the slowest, of course, the onboard charger, and the fastest, the battery swap. Here is an example of the power converter used for an onboard charger, and there's an illustration how it fits, what fits inside the car and what fits outside the car. This one is by Costal, and this is a fourth generation onboard charger, 11 kilowatt power. This is a quite big one. And it's composed of 3 LLC resonant full bridges connected in parallel to reach that power level. And as you can see, it fits in this box over here inside the vehicle. Of course, onboard chargers are smaller in power because they have to fit inside. If we go off-board charger, this is the one with low frequency isolation. This is an example by Porsche. This is a Porsche power box. And this one has a 12 pulse diode rectifier and transformer system, and then you have a boost power factor correction and a buck DC-DC converter, and they can be arranged in parallel or in series to reach higher voltage levels. This is because Porsche has introduced the 900 volt battery in their Porsche Taycan, and this gives the flexibility to this charger to reach all the range in voltage levels for different voltage batteries. And this is an example of an off-board charger, but with high frequency isolation. This one is by ABB. It has 6 of these 30 kilowatts PEBs, which is power electronic building blocks, connected in parallel to reach this power level over here of 180 kilowatts. And it's made of an LC resonant half bridge converters. If we go to heavy duty vehicles, buses and trucks, you can see that heavy duty trucks can be also connected to depot chargers, similar to the fast chargers, the DC fast chargers we saw earlier for cars, only that these are a little bit higher in power, usually 400 kilowatt currently, but they are expected to grow even over the megawatt range. But they can also have opportunity charging or dynamic charging, which is while the vehicle is on the road. And here it can be with a pantograph, like you can see here on this picture of a supercab bus, which actually has no batteries, but supercabs, and you charge the necessary amount of energy you need from going to station, or with a catenary, as this one seen here with the truck. This is an example of a heavy-duty fast charger. This is a 1.2 megawatt example by NREL in the US. And to reach these voltage levels and power levels, you need this modularity to get to that power level and to this voltage range. If you want to have more detailed look at power converter topologies, you could refer to this paper over here, which is also authored by many of the authors of this of the paper of this special issue, where you can see a lot of commercial topologies for onboard, integrated, and offboard chargers. I won't go into detail, but as you can see, power electronics is the main technology here, of course. And if we go to the to the standards, you can see a lot of AC standards. So as you can see, AC charging is really low in power, from 2 kilowatt to a few tens of kilowatts. The largest one is around 166 kilowatts. And here you can see the different connectors. There are different protocols for different countries and different voltage levels. So this is one of the main issues with charging infrastructure. If we go to DC charging, we have JADEMO, which is from Japan, GB from China, and CCS2 from Europe, also used in most of the world, and of course the Tesla, which is a proprietary one. And here in DC fast charging, you can really see reaching 400 kilowatts, which is the third generation of fast charging, and also reaching 1000 volt, which is the current standards in the biggest batteries. Most of the cars still have 400 volt batteries, but they're moving to 1000 volts to increase efficiency and reduce charging times. You can see that again, all the connectors are way different one of the other. And these are the three standards that currently coexist for heavy duty. So the one that has become more widespread is the megawatt charging system from Charin, and this one could even reach 3.7 megawatt in charging charging power. So if we look at trends and future outlook, the increase in the battery voltage is still a trend. So currently we have 400 volt and 800 volt batteries, but there are some talks and developments going to 1500 volts, which would further reduce cable size and increase speeds and increase efficiency. But this poses a challenge, which is how we can achieve such charging stations that could provide power across the whole voltage range. So power electronics is not that good at elevating or reducing voltage compared to traditional transformers. So here we have to go into the electronic transformer range and use power electronics wisely to retain efficiency and be reliable. So that's still a big challenge. If we go, the efficiency, of course, power density and reliability still remain one of the main drivers in development area, particularly reliability, as when electric vehicles become more widespread adopted, and we will have more charging stations. People wouldn't like to get to a charging station and have 2 or 3 chargers being down because of maintenance or failure issues. So power electronics is, as Professor Bladwick showed, is now everywhere, and so reliability has really become the biggest issue regarding power electronics because of that, because it has become a critical technology. Battery swapping remains something that looks interesting. So NIO is an electric vehicle company from China, and they're doing very well in China. They are now entering Europe, I believe, in the Netherlands. But battery swapping has this issue that you need more lithium because you need some battery redundancy in order to have a battery on the car, on the street, while you're charging one. So it's not that you need to duplicate every battery in the market, but you still will need more batteries and therefore more lithium. And there are some studies that said that lithium might not be enough to do all the electrification that is needed, not just for transportation, but for other energy transition applications. So that could become an issue in the long term. So battery swapping is very convenient in terms of charging times, but it has that issue. In terms of wireless charging, that's also a very promising technology with a lot of challenges. Here we have static charging, which is while the vehicle is not moving, like in a parking space or traffic lights. And we have the dynamic charger, which is when the vehicle is moving, so in highways and streets. And it has a lot of, it's very appealing, of course, because you forget about the connectors, you forget about the charging. Even this is way more attractive than gas stations. So you forget about energy in your car, basically. But of course, to do that, you have the challenges that come along with that, which is the extra cost in infrastructure. So you need here really to change highways, and so there's a lot of cost in related to that. And the other issue is, of course, the efficiency. So it's always less efficient to transmit power through air, and also you would inherently have a slower charge. So we don't have such high power capabilities to transfer power through air. And lastly, the levels of grid integration. So vehicle to grid is something that has been in research for a few years, and it's still a long way to go. So vehicle to grid and vehicle to X, really, which is vehicle to any kind of other application, is really where we can use the batteries available in all the electric vehicles to actually provide services to the grid. So we could we could provide frequency regulation. We could also do energy storage and so forth. Many levels of integration, but that requires bidirectional power flow and also level of integration and level of coordination with the grid operator that requires, of course, standards and regulation. And in the paper, we have included a few topologies, and when the car is connected or disconnected, which are the services that this kind of configuration could provide to the grid. And as you can see, of course, diode-based converters are not bidirectional and cannot provide many of these services. That's why they're in red. And when you move to fully controlled converters, you can get in the green range, where they can provide a few of these grid services, both when the car is connected or even when the car is disconnected. When the car is not connected, and even if you don't have a battery, the converter can provide, for example, act as an active filter and do some harmonic compensations and stuff like that. And there are some even chargers that come along with batteries. So even when the car is not connected, like this one over here, you could provide black start support and other services that could be given by the battery of the charger. So as a summary, we have come a long way in terms of electrification of electric vehicles, and even though the charging infrastructure is really moving fast and it's getting more mature, there's still a lot of development going on, and there's still a lot of issues that need to be tackled with. As you can see, it's not heavily penetrated in all the countries around the world. There are particularly many things related to regulation and integration of different standards. And there are also a lot of R&D trends, like higher and wider voltage operating range, topics regarding efficiency, power density, reliability, etc. And that gives us, plenty of room for R&D and technology transfer for the next 10 years.